22.2, using electrical energy. What we've been talking about in our introduction to chapter 22 was the use of voltage and how voltage is related to current and resistance, and how we can change current, we can change resistance, and kind of the combination together for Ohm's law. So how do we actually use this electrical energy? Well, what we have is energy is obviously transferred in electrical circuits. What happens is anytime electricity goes through a resistor, it generates heat, and we know that heat and electricity are types of energy. So current moves through the resistor and causes heat, and we've talked about the resistor is because it's very similar to friction. So what happens is, how do we use this? Your guys' everyday applications use this. Hot plates, hair dryers use this, where they have a coil with a built-in resistor. Electricity goes through them and they warm up. And you can calculate the power a resistor puts out. So what is that equation? Power is equal to I squared times R. So we're going to take the current and square it and times it, or sorry, yeah, the current and square it and multiply it by the resistance. So P is equal to I squared times R. So we're going to get a couple additional equations for power when we go through here. Power, we can also relate voltage and resistance when we are talking about power. Voltage and resistance. And when we do that, power is equal to V squared divided by R. So a couple multiple ways in which we can solve for power. Either P is equal to I squared times R, or P is equal to V squared divided by R. Thermal energy, if power continues to dissipate or lose, the energy will be converted to thermal energy, which is heat, which is a resistor creating heat. Old school light bulbs, not the new type that are being introduced this year, but old school light bulbs with a filament were not very efficient, simply because all that electrical energy was being converted to thermal energy and creating large amounts of heat. When we talk about thermal energy, there's kind of three equations that we can use. They're all the same. And the reason they're all the same is what I've done is E is equal to P times T. What I've done is I've plugged both our definitions of P in. So either one. I would really just stick with the top one. E is equal to P times T. Power times time. Power times time. Now the units for this are going to be a little goofy. Superconductors, zero resistance. You can kind of talk about, that's kind of common sense there, something that doesn't have resistance. Should have put that below, because as we talk about energy, energy for the most part by electric companies is measured in a little different unit. It's measured in a kilowatt hour. And electric companies charge you based on the amount of kilowatt hours that you use energy-wise. So a kilowatt hour is 1,000 watts delivered for 3,600 seconds, which is 1 hour. So when you solve for energy, a lot of times the unit is in a kilowatt hour. So when you have P, you want to make sure your P is in kilowatts and your T, your time, is in hours. So just kind of make sure that that's what you do. So kilowatt hours. An electric company gets away with charging you like to the 5th decimal point per kilowatt hour. Like each kilowatt hour costs 8.62432 cents. I don't know how people can get away charging decimals of a cent. It doesn't even exist. So they make more money every month off of you doing that. It's one of my big pet peeves. So we'll move to the example. Example, what power is dissipated in a heater when a resistance of 10 ohms in an American household circuit, which is 110 volts. Our voltage is 110. Our resistance is 10 ohms. What is our power? Remember, we have three equations to choose for power. One of them is power is equal to V squared over R. That would be 110 squared over 10.0. And when we do that with sig figs, 110 only has 2 sig figs. So our answer is going to be 1200, and the unit for power is watts. So that is part 1. Part 2. What thermal energy is supplied by the heater in 10 seconds? Well, now we want our thermal energy. Well, thermal energy, E, is equal to P times T. We know our power from the previous part is 1200 watts, but remember, energy likes to be expressed in kilowatt hours when we're talking about electrical energy. So power is equal to 1.2. Our time is 10 seconds. However, we need to get that into hours. So we're going to take 10.0 and divide by 3600. And when you do that, you're going to get 0.0028. And you are going to put those together. Power, which is 1.2, times our time, 0.0028, is equal to 0.003. And technically, we could do 3 sig figs, so 2 sig figs, 0.30. And our unit, as we talked about with electrical energy, is a kilowatt hour. Believe it or not, that concludes chapter 22. That summarizes everything that we need to do with voltage, current, resistance, power, and electrical energy, all those wrapped into one. So you have a worksheet on that material tomorrow.